Hi everybody. This is the lecture on section 6.1 on vector fields. Before we start in on chapter 6, let me mention to you that the material here conceptually is going to be even more challenging than it was in chapters chapter 5 and chapter 4. So you're going to need to spend a little bit more time with it. Computationally, it's not as hard, but the concepts and the setups are again, what we're really testing you on in this course. All right, so what is a vector field? A vector function, so a two-dimensional vector field is of the form, is a vector function of the form capital F of x, y equal to p of xy, that's a two-variable function, and q of xy. So these are just ordinary two-variable functions as the x and y component of a vector function. And a three-dimensional vector field is a vector function f of x, y, z equal to p x, y, z, q x, y, z, r x, y, z. Okay, so same idea. It's a three-dimensional vector function with three variables as inputs. Okay, and what a vector field does associates a vector at each point in space where that vector at, coordinate AB, or ABC is f of AB or f of A, B, C. So whether you're in 2 dimensions or 3 dimensions here. So for example, consider just this very simple fxy equal to minus x comma y. Okay, notice that, right, the vector xy, which is just the vector from the origin to the point xy, dot I did that wrong, minus y comma x. Dot minus y comma x is equal to, well, it's minus xy plus xy is 0. So each vector in the vector field, right, if this is the point xy right here, then this is the function f, or the vector f. This is the vector xy right here. Now at that point xy, we want to associate f of x. So that's the vector of the exact same length orthogonal to this one, and pointing in this direction rather than the opposite one. So this is fxy equal to minus yx. So the way the vector field kind of looks is as follows. is as follows. So here is an XY plane. Now, let's take the circle whose radius is, let's say this is radius equal to 1/2. And this here is going to be, well, I guess we'll just do 1. This is radius equal to 1. Over here we've got the circle of radius 2, centered at the origin. This is the circle of radius 3. So we've got these circles centered at the origin. And at every point on the circle, the length of the vector from here to here, is just the radius of that circle. And so this vector, right, this is the vector, say, xy. For this point right here, xy. So we're going to have the same vector, 90 degrees, which is tangent to that circle, pointing in this direction. So the vector field is a bunch of tangents to this circle, sort of indicating a direction of rotation. So these vectors here have length 1, length 1, length 1, length 1, all tangents to the circle. These vectors here have length 2 on the circle of radius 2. And then here, these vectors have length 3. Tangent to the circle having length 3. Actually, this one is going to be just like that. So that one's a little bit long. As is this. There we go. Length 3, length 3, length 3. All right, so this is the vector field that we have. That's the way it looks like for the vector function fxy equal to bracket minus y comma x. Right, it's kind of got that nice whirlpool effect going there. All right. How about the following? Something a little similar to that. What would this vector field look like? So sketch the vector field. fxy equal to minus y over square root x squared plus y squared, x over square root x squared plus y squared. Notice that for every x and y, okay, the length of fxy is equal to, well, it's the length of this vector here. Right, which is equal to what? You have to square each component, add them together, take the square root. So I have y squared over x squared plus y squared. plus x squared over x squared plus y squared. And this is just equal to square root x squared plus y squared over x squared plus y squared equals 1. So for every xy, the vector in the vector field has length 1. Okay, such a vector field is called a unit vector field, obviously, because every vector in the vector field has length 1. So a vector field in which for all xy is called a unit vector field. All right. So fxy equal to 1 for all xy, or fxyz equal to 1 for all xyz. Is called a unit vector field. And how does this unit vector field work? What does it look like? Well, the sketch for this unit vector field is the same as the sketch for this vector field, except all those vectors shown have length 1. So length 1, length 1, length 1, length 1, 1, 1, and then these are still length 1. They point in the same direction. As with the previous vector field, but they're all divided by their own length. Right? So it's just the vector minus yx divided by the length of minus yx, which we know to be a unit vector, a vector of length 1. So this is a unit vector field. Okay, so there's a depiction of that one. A specific type of vector field is an important one. Given a two-variable function, f of x, y, or a three-variable function, f, x, y, z, a gradient vector field is a vector field, a gradient vector field with potential function f. Is as follows. So we write it as gradient f x y, and then this is partial derivative of f with respect to x, xy, and partial derivative of f with respect to y at xy. Right? Or for the three variable function f, x, y, z, this is equal to gradient partial derivative of f with respect to x, partial derivative of y with respect to x, and partial derivative of z with respect to x. And remember that the gradient vector field, represents the gradient function, gradient vector of that function at any given point. And that's always perpendicular to the level curves of the function itself. So, for example, that the level curve k equal to f, x, y, right, or the level surface z equal to, k equal to f, x, y, z in 3 dimensions is perpendicular to the gradient vector, depending on which one is appropriate, the 2 variable or the 3 variable. So, for example, if I had f of xy equal to x squared over 9 plus y squared over 4, so if you took this 2 variable function here, then what do the level curves look like? Well, the level curves are going to be, right, for z equal to 0, you're just going to have 0. And then for z equal to 1, you're going to have the ellipse whose radius on the y-axis is 2 and on the x-axis is 3. You get this ellipse here. So that's for z equal to 1. And then for z equal to 2, 3, and higher, you have various ellipses that share the same rough proportions of this one here. So that was z equal to 1, this is z equal to, I don't know, z equal to 2 perhaps. It'd be right here, all ellipses. Now the gradient vector field, so these are the level curves. The gradient vector field is going to be what? Well, the partial derivative of f with respect to x, which is going to be 2 over 9 x plus 0, comma, the partial derivative of f with respect to y, which is going to be a half y plus 0. So that is the gradient vector field, and that's what it looks like as an arithmetic expression. And then, come on. If we're to draw it, it remains perpendicular at every point. right? So perpendicular at every point to the level curves themselves. That's not really perpendicular there. Here we are. Here it's going to be pointing straight down, so on and so forth. Okay, so the gradient vector field, okay, either in 2 dimensions or 3 dimensions. You have a two-dimensional, a 2-variable function or a 3-variable function, and then its gradient expression, right, is a gradient vector field, and then the function f is called the potential function for that vector field, and then you always get a vector field where each vector is perpendicular to the level curve that goes through that point there. Okay. Now, gradient vector fields are going to be important later in Chapter 6, as you'll see. So, having a way to verify if a given vector field, without any mention of a potential function, actually is a gradient field, it would be helpful to have a method for doing that, for detecting that. So, a vector field f of xy or f of xyz is said to be conservative when it has a potential function. fxy or fxyz. That is, f of xy is equal to the gradient of that potential function, or f of xyz is the gradient field of the 3-variable function. So remember Clairaut's theorem. Right? Clairaut's theorem was that when when f, let's just say f, has continuous first partial derivatives, then fxy equals fyx. Right, so that's for a 2-variable function. As continuous first partial derivatives, then fxy equals fyx. You can generalize that to 3 dimensions when fxyz has continuous first partial derivatives. Then the second derivative is fxy is equal to fyx, fxz is equal to fzx, and then fyz equals fzy. Okay, so given a fxy, right, this is equal to fx, fy. It's the vector field given by the partial derivatives, partial derivative of x in the x-coordinate, partial derivative of y in the y-coordinate. So if we let P equal fx and Q equal fy, then, right, the derivative of P with respect to y, which is fxy, is equal to fyx is equal to the derivative of Q with respect to x. So, oops, this is gradient. I wrote that all wrong, didn't I? Let's redo that. Given a function fxy, the gradient field is right, and if we let P comma Q equal fx fy, then the derivative of P with respect to y is fxy, which is equal to, by Clairaut's theorem, fyx, which is equal to qx. Right? So you need equality of the partial derivatives P and Q when you are a gradient vector field. Therefore, we get the following theorem. Therefore, if a gradient vector field, a vector field equal to pxy qxy. So if you have a vector field, fxy is equal to p comma q, and the derivative of p with respect to y is not equal to the derivative of q with respect to x, then f is not conservative. Then f is not conservative. Now, actually it works the other way around as well, and we'll talk more about that in subsequent sections, but for now we'll just go with this, okay? If you have that a vector field f, p comma q, has the derivative of p with respect to y not equal to the derivative of q with respect to x, then it's not conservative. It's not the gradient field for any possible potential function. Because if it was, right, then py would be the potential function partial derivative with respect to x. So py would be fxy, which is equal to fyx by Clairaut's theorem, which should be equal to the derivative of q with respect to x. So when it's not the case, it's not conservative. So for example, fxy equal to this little whirlpool vector function that we've been working with here, vector field we've been working with here. When you have fxy equal to this, it's not conservative. Because the partial derivative with respect to y of this, p, right, is equal to -1. And the partial derivative with respect to x of this second, the q, is equal to 1. And they're not equal. Right? So, not a conservative vector field. For three-dimensional vector functions, f, x, y, z, okay, the gradient let P, Q, R equal this gradient of f, which is equal to partial f with respect to x, partial f with respect to y, partial f with respect to z. Now, let this be equal to that, and take this new vector, just call it triangle or gradient or whatever, and let that just be the vector of differential operators, partial with respect to x, partial with respect to y, partial with respect to z. So let PQR equal fx, fy, fz, and partial, just this triangle down, is equal to the vector of differential operators like that. Now, consider the cross product. PQR cross, or let's do it the other way around. Cross this. Well, that's I, J, K, partial with respect to x, partial with respect to y, partial with respect to z, P, Q, R. Right, it's the determinant of this 3 by 3, which is equal to the partial of r with respect to y, partial q with respect to z. ry minus qz. And then in the next coordinate, it is pz minus rx. And in the k coordinate, it's qx minus py. Right? Now, what was r? R is fz. So this is fz. So this is fzy. And q is fy. So this is fyz. Right? This is fxz, fzx. This is fyx, fxy, which by Clairaut's theorem is 0, 0, 0. Okay, so given a three-dimensional vector field, PQR, if this cross product is not 0, it can't be conservative. Therefore, given a vector field, three-dimensional vector field, fxyz equal to PQR, if gradient cross f is not equal to 0, 0, 0, then f is not conservative. Not conservative. Okay? Actually, it works the other way around as well. If this is equal to 0, if gradient cross f is equal to 0, then f is conservative. But we'll talk more about that later. For now, it's just a test for not being conservative. Okay, so so it's a little more complicated in the three-dimensional case. It uses a cross product, but it still makes a lot of intuitive sense there. Okay, so that's all for the lecture on section 6.1. We'll have the lecture for section 6.2 up very soon.